Hi, this short video is to help you use the bayesfactor.info calculator. The web address is bayesfactor.info and I've got it up on the screen here. The reason we generally want to use Bayes factors is that they provide a more direct answer to the questions that we're asking when we do studies involving statistics. And unfortunately, even now, even highly trained and experienced researchers misinterpret the results of classical statistics, and that leads to conclusions which can then lead to false decision-making. Bayes factors are designed to provide people with the information they need from a study or a series of studies to make good decisions based on data. In this website, you can click on the About section, and it just gives you a very brief introduction to the use of Bayes factors. And in the captions, you'll see a reference to an article which provides more information on this in the field of addiction, but the same principles apply elsewhere. So when you calculate a Bayes factor, what you're trying to do is to establish what is the relative likelihood of a particular hypothesis, let's call it H1, your experimental hypothesis, compared with another hypothesis, let's call it H0. And very often that H0 hypothesis is what we would call in classical statistics the null hypothesis. The hypothesis that there's no effect, no difference, no relationship, and so on. That whatever parameter estimate we're interested in, it reflects the fact that two groups or two sets of data are the same. The H1 very often is that a particular set of numbers is larger than another. For example, if you've got a randomized controlled trial with an active treatment and a control, then what you're often interested in is the active treatment more effective than the control, which might be a placebo, for example. Now, what you very often find is that when people get a non-statistically significant difference between the experimental group and the control, or a non-statistically significant relationship, then they, despite what they're told, even as undergraduates in the first year of doing any statistics course, they often conclude that this means that there's no difference. Now, you can't conclude that unless you calculate a Bayes factor, in which case you can assess evidence for the null versus the experimental hypothesis. So one important reason for using Bayes factors is to differentiate results that genuinely show that there's no difference, or it's very unlikely that there's a difference between your conditions, or very unlikely that there's an effect or a relationship, from one in which actually the reality is, if anything, that the data point in the direction of there being an effect, or in the direction of there being no effect. But either way, it's not conclusive, but it's a pointer. So let's just take an example just to start things off, and let's look at odds ratios or risk ratios. So these are numbers taken from a randomized trial comparing a drug called cytosine for smoking cessation versus placebo. So it's a double-blind, placebo-controlled randomized trial. And in that trial, they observed a risk ratio. And the risk ratio that they observed was, in fact, 1.12. And that wasn't statistically significant. Now, in that case, the authors, who are a very experienced and highly competent group of researchers, concluded on the basis of that, because it wasn't statistically significant, that the that cytosine was not, they concluded quite definitely that cytosine was not more effective than placebo in this particular group of patients. If we look at the main results table here, then in fact you can see that probably the most important outcomes would be continuous abstinence at 12 months, that's the longest follow-up period, biochemically verified, that's this one here. And you can see that their odds rate, their actually risk ratio was 1.12, and the confidence intervals were 0.97 to 1.29. So because the 95% confidence intervals span 1, which would be no effect, they concluded no effect. But okay, let's go back to the bayesfactor.info website. So we can just put in the upper confidence interval here, 1.29. And then let's see, well, what's the hypothesis under test? Well, I've put in here 1.5. So that would be the hypothesis, which would be a perfectly reasonable hypothesis, that that cytosine increased the success rates of this particular group of patients by 50%. Okay, so let's see whether that hypothesis is actually borne out or not borne out, or whether the data are inconclusive. And it's one-tailed because we're expecting cytosine to do better than placebo. So you calculate it, and it comes up with a Bayes factor of 1.09. Well, a Bayes factor is in effect a likelihood ratio, so that if the Bayes factor had come out as 1, that would mean that the likelihood of H1 versus H0 was exactly the same. There was really nothing to choose between them on the basis of these data. That would mean that that having done this study, we would have to say that we actually know no more than we did before we did the study, which happens. You know, it's when you do studies, sometimes you get clear results and sometimes you don't. In this case, it's actually very close to 1. It's slightly higher than 1. So there's about a 9% percentage point, or 9% chance, if you like, greater than that the cytosine had an effect of in the region of 1.5 versus that the effect was 0, or the risk ratio was 1. So what that means is that if anything, the data very, very marginally point to the hypothesis under test being more likely than the null hypothesis. If we had wanted to conclude, as the authors did, that the null hypothesis was more likely than the experimental hypothesis, and with the degree of certainty, then you'd really want a Bayes factor certainly less than 0.3. That's one of the classic sort of thresholds, that if you want to assert the null with some moderate degree of confidence, then you would need a Bayes factor of less than 0.3. In other words, that it's less than 30% likely that the experimental hypothesis is true relative to the null. On the other hand, if you wanted to assert that the experimental hypothesis was more likely to be true than the null, you'd be looking at a Bayes factor of at least 3. And that's sort of somewhere in the same zone as the 0.05 level of significance. It's not a massively high degree of confidence either way, but it's a pretty high. Now, this is nowhere near that, and that shows that actually it is statistically completely wrong to say that in this case that the data show that cytosine is not more effective in this group of patients than placebo. Let's just mess around with the figures a bit, just to show what might happen, or under what circumstances that conclusion might be justified. Let's say that we'd found that the risk ratio was, let's say, 1.03, really close to 1. And let's say the upper confidence interval was the same, what would that give us? Okay, so even if with that we had found that really, what would feel like very compelling evidence that there was no effect of this drug versus placebo, with a pretty large sample, then you're not really meeting the threshold for concluding that that cytosine doesn't have an effect. There's still, room for doubt about that. Let's go back to 0.1 and see what happens there. And even there, but let's say that you actually got an odds ratio that's slightly less than 1. Now you're in the sort of ballpark where you could say with some degree of confidence that there was no effect of cytosine. So what you can see is even when the data look very compelling to you as a researcher, that there's really no effect there, you can't conclude that by eyeballing it, and you certainly can't conclude it on the basis that you didn't find a statistically significant difference. You've really got to calculate a Bayes factor in order to be able to make that kind of assertion. And so hopefully using this website, not only can you as a researcher interpret your data more accurately, but when you're reading conclusions from research papers or doing reviews, you can also using it with other people's data to see whether their conclusions are justified. That was using odds ratios and risk ratios, but you can also look at mean differences. If I untick that box, it'll give you mean differences. Now, so for example, let's suppose I did a study looking at the impact of taking caffeine versus placebo on on visual reaction time, and let's say the difference was let's say 0.2. I've written it here. Seconds. You can then put the standard error in instead of the upper confidence interval. So if your t was let's say 1.7, then the standard error would be 0.2 divided by 1.7. So let's put a standard error in here, and let's just call it 0.02, for example. And you always have to put your H1, your hypothesis, under test. In effect, what you're testing is a range of values. You don't have to be precise about it. Say, well, it's definitely, I would definitely expect it to be 0.3 or 0.1 or whatever it might be. You can specify a distribution. By default, bayesfactor.info specifies a normal distribution with a scale factor or a standard deviation of your hypothesis mean difference. So hypothesized mean difference. So if your hypothesized mean difference is, let's say, 0.3, that's what you thought it would be, then this simple version of it will say, well, our H1 hypothesis is that there will be a difference in reaction times, and it will be somewhere between 0 or just above 0 and some value tailing off as a normal distribution does, but with a standard deviation of 3. So if you say this is what I think the mean difference is going to be, about 0.3, then you can just put it in here, and it's not saying it'll be exactly that, it's saying it will be in a distribution that has that standard deviation. And because we're expecting it to be one-sided, to go one way, we call it one-tail test, and we calculate it, and boy, do we get a big Bayes factor. So that is very clearly supported, that hypothesis. That is definitely more than 3. Let's make the standard error a bit more realistic. Let's call it 0.1, recalculate it. It's still looking pretty promising, so it's still supporting the hypothesis, okay? If the Bayes factor, if the standard error was, let's say, 0.6, then you can see that the data are equivocal. very, very nearly 1. That's the ratio of the likelihood of the experimental hypothesis being true versus the null is about 1. So you can see it's obviously responding as you would hope it would to the size of the standard error. The smaller the standard error, the more confident you can be that whatever figure you've got is the right one. And it'll also respond obviously to the size of the effect. So, and let's say we had found with that standard error, actually really no difference at all. It was just naught here. What would that mean? Okay, even then, you can see, even then, you would not be justified in concluding that there's no effect, because even though you didn't actually find any difference at all, your standard error is such that you cannot be confident that, that there was no effect of caffeine. You just have to bite the bullet and say that the data were insensitive in this particular experiment. So it's really probably mostly when it comes to interpreting negative results that Bayes factors really come into their own. But actually there's so much more use for them, and they're so much more useful in general than classical statistical tests. I would always recommend using them. And this calculator gives you a really easy way of doing it. I'm just going to finish with showing you some detailed options for the power users. So when you click on detailed options here, then you get a number of different things that you can put in terms of your distribution. Here we've still got talking about our mean difference and our standard error, but we could say, well, okay, what is the actual distribution of our data here? What's the likelihood distribution here? Is it a normal distribution, or do we want to use a student's t-distribution? It makes a little bit of a difference to the Bayes factor, can do, depending on the situation. Student's t-distribution is one which is typically more pointy than a normal distribution and would be probably more relevant when you've got small sample sizes. I could just show you what that looks like if you use a student's t-distribution here. You can see it doesn't make a lot of difference in this case, but you've got the option of doing that. So this is the distribution of your data. So note obviously that if you're using risk ratios or odds ratios, then it's not going to give you options here because you're basically converting from an odds ratio to what will be a normal distribution using logs. So, but let's take this back to mean differences again. That's the distribution of your data. What's also quite useful about this website is that you can specify here the distribution of your hypothesis under test. So I mentioned before that we were using a hypothesis which was the H1, which was you'd start at 0 and it'd be half normal with a standard deviation equal to the scale factor, which is our hypothesized difference here. That's one kind. We can also specify as our hypothetical distribution, our experimental hypothesis, a t-distribution, which is more pointy. We can specify what's known as a Cauchy distribution, which is a t-distribution with 1 degree of freedom. And you can specify a uniform distribution, in which case it'll ask you what your upper and lower boundaries are. What are the outside ranges within which you think the value will lie? So you could go from, so your experimental hypothesis might be, I think it's going to be anywhere between 0.01 and it's just marginally greater than 1, and let's say 0.5 here. And then you can calculate that. And you can see you get a Bayes factor of 0.3. So depending on what you do, it may change or it may not. But you can mess around with it and see what different hypotheses under test produce in terms of results. So if I then just go back to, but still with the detailed options, looking at odds ratios or risk ratios, then again, you've got the options here of specifying a normal distribution, students T or Cauchy, for your experimental hypothesis. Quite often with odds ratios or risk ratios, it makes sense to specify a lower and upper bound. So you'd say, well, I'm interested in any effect that would be from 0.101, anything better than 1. And I think the largest effect that I'm ever likely to see is 5, let's say. And you can see, well, that in that case, with this odds, with this risk ratio, and with that upper 95% confidence interval, that's very unlikely. But if it was, let's say, 2, it would be a bit less unlikely. So you can see how it makes sense. And what you're doing is you're getting really much closer to what we really need to do in science, which is when we're hypothesis testing, is to say, well, what is the hypothesis? And what is the likelihood of that hypothesis relative to some other hypothesis? As I say, often what's known as the null hypothesis. So that's it. That's how to use it. I do recommend using it in your own research, but also when you're interpreting other people's research. And hopefully we can reduce the extent to which people make this unfortunate mistake of concluding no effect when what they've got is no statistically significant difference between two groups. Anyway, that's it. Have fun with it. And feel free to email me. The email is in the caption here. And thanks very much to Harry Tatnam-Birch and Zoltan Dinesh, whose work this all is. And Harry, who's working at UCL, wrote all the code for this. You can see it here. It does a lot of calls to procedures in R. And Zoltan is maestro of Bayes factors. Look him up on the internet. He's really, really good. And also special thanks to Bence Palfy, who was very helpful in creating this website. Okay, that's it. Have fun.